Afternoon, everyone, and welcome back to another round of Still Connect webinar. I'm Rocky and your host today to talk about 4 criteria of external cladding design to extend its lifespan. So when we think about external cladding, most often is referring to roof and wall cladding. So it's quite common that we refer to steel roofing and steel wall cladding. So in our previous topics, we covered different usage of steel cladding and how it can cater to different building designs, such as using it for external cladding or using it as a platform for solar panels. So you can refer to our previous webinar video on our platform. So there are studies that are done by us that shows that a proper steel cladding can actually last for more than decades without sign of rust, even in the coastal region, and yet still present you with an excellent appearance to function as external cladding. Or this type of steel roofing also can be used for covering of factories, as shown in this example. So this example itself is actually covering an automotive factory and has been there for more than 20 years, but it is still showing a really good condition. It's expected to last for another 2 decades. Or this chalet near the sea, which still provide not only a stable shelter, but also a good appearance to the overall building. So all these roof and wall cladding are actually designed not only for long-lasting, using long-lasting material, but it can also, if paid good attention to the details of design, can achieve even longer-lasting lifespan. So what are the design criteria that you need to pay attention to or consult an experienced expert to achieve such longer lifespan? So let's get into it. Okay, so for those who are not aware, so let me just share a bit insight of what is a flat roof design. So in the recent decade, we know that flat roof has been widely used and widely adopted for many types of building designs, especially in the residential area where flat roof is used to achieve building blocks design, like the one that's shown in this picture. So this kind of design was trendy in the past decade and especially adopted by most of the large housing development companies. But at the same time, it actually can achieve functional value where it can actually maximize the usage of the second floor, third floor space, where it used to be a pitch roof where you can only have half a floor. Now you can actually maximize it to a full floor. So places like the attic space can become a full utilizable floor. So what is flat roof exactly? So essentially, if you search online definition of flat roof, what it means is the roof pitch actually is near to horizontal, but it is not exactly 0 degree. So when people refer to flat roof, when we refer to flat roof, what we mean is it is not 0 degree roof, okay, not flat, but rather it will have a certain degree from horizontal surface. Okay, so this is one of the example that's shown in this diagram. At least there's a certain angle to it. So this angle itself is what we call a roof pitch. So the roof pitch itself can be measured and it can be defined in such a way where you put the ratio of rise, as can be seen from this diagram, the height of the roof to the run of the roof, which is the length of the roof. So these are terms that are used in the roofing industry. Okay. So in order for you to determine the angle, right, you actually use this formula that is, I believe, can use the trigonometric formula. Tangent of this angle is actually equal to the ratio of rise to run. Okay. So aside from representing roof pitch in angle or degree, you can also represent it in the ratio form, which is rise over run. So I've shown these 2 examples. So the first example is that 1/12 can actually mean that 1 meter over 12-meter run, 1 meter rise over 12-meter run. And another example that I'm showing here is 12 by 12. So what this means is that you have a 12-meter rise over 12-meter run. And essentially this means 45-degree pitch, roof pitch. So why would you want to determine the roof pitch? Right? So well, these questions will have to do with the weather and mostly experienced by tropical countries like us. So the one critical characteristics of the weather is rain in tropical country. So by determining the roof pitch, you are able to determine how the roof reacts to rainy days, during rainy days. So, for example, if let's say I have two different roof pitch, one I consider it high pitch roof, another one is low pitch roof. So, when these two roofs are exposed to the same rain intensity, the one that has a higher roof pitch will normally have a faster water flow. So, in a way, the water will not be lingering or most of it will flow faster down to the drain or to gutter. So in a way, you also can describe it as the water level on top of the roof during the rain will be lower compared to a low pitch roof. So if let's say I were to use this roof cladding profile, right? So if let's say the water does not run faster than the rain intensity, then essentially what you have is water level rising above the profile and then submerging the profile. And this will present a risk of leakages if let's say the water level rise beyond above the roof profile height. So in this case, you have to also look at the type of profile, so the rib height, so-called. So here I show you three examples of profile rib height. So each of them from the top, which has the highest rib height of around 90 mm or sometimes even higher, okay? And all the way down to the lowest, which typically around 25 mm. So these different rib height will react differently rainy days. Okay, so here I took a chance to actually draw the diagram. And here you can see that in the same condition, different profile would cater to water runoff differently. So with the same rain intensity, maybe for the low rib height profile, the water might overflow. But if let's say you change it to a high rib height profile or high rib profile, then the water itself will not submerge the whole rib. And in doing so, water will not be able to seep in through the gaps of the roofing sheets. So by doing that, then you prevent water leakage through the roof. So of course, most manufacturers or experts, when they sell this, there are different types of profile. They will actually show their recommended roof pitch, and then also normally they will state what is their rib height. So over here in this example, you can see that the rib height is around 20 over, and the recommended roof pitch is around 3 degrees minimum. Okay, and here is another example. So noticeably, you can see the rib height is increased to 43 mm, and this is a concealed fixed profile. And by having a higher rib height, you can see that the minimum recommended roof pitch lower down to 2 degree. And over here, you can also see the ratio of 1 in 30. So this means 1 to 31 can be 1 meter rise to 30-meter run. So that is the ratio. But again, come back to the roof pitch, right? Due to the constant climate change, you might, when you're considering roof pitch, this kind of climate change can actually affect your decision. So when rainfall intensity compared to now to 5 years or 10 years ago, the rainfall intensity now it is definitely much more higher compared to 5 or 10 years ago. So the recommendation or the research done, recommended by all these manufacturers 5 or 10 years ago might not be, safely applicable now. So what you need to do is go back to, all these reputable manufacturers and ask them what are the recommended roof pitch that is suitable for the current weather, right? So why now current weather you should actually look for higher roof pitch, but there's another diagram that I'll show you later. So in this case, when there's actually changing weather, you have to consider also how big is your roof or how big is your floor space, right? So to cater for the minimum roof pitch that is suitable for. So because longer roof normally will need a higher ridge profile to cater for water runoff, as the water at the ridge is required to travel further to reach to the gutter. Okay. So for you to make the right choice in determining the roof pitch, you should consult your roof formers to actually calculate based on the rainfall intensity what's the most suitable roof pitch and profile type you should select. So just like the previous example, higher ridge profile will be able to cater for longer roof run given the same roof pitch. So here I'm showing you two different types of profile, one at a higher rib height, the top at a higher rib height, and then the bottom one at a lower rib height of 24 mm. And similarly, we are actually comparing the rainfall intensity of 300 to 400 mm per hour. And you can see that with the same roof pitch of 3 degree, the higher rib height can actually have a maximum roof length. That means if let's say your building is around 50 meter long, then you can actually consider using the higher rib height one instead of the lower rib height one. Of course, if let's say you go even higher rib height of concealed fix of 43 mm, then the roof line can essentially go more than 100 meter, so without any risk of and overflowing. Okay. So this is based on 3 degree roof pitch. So with that, we actually did some study on this, and this is actually an airplane hangar at KLIA. As you can see, the roof pitch itself is very low, and the roof run is actually over 100 meter length. Okay, one side. So the roof is actually made of very, very deep corrugated profile with rib height of over 98 mm. So it is double of the concealed fix that I showed you earlier. So as you can see, it's actually a single length roof, so no lapping for the entire roof run. So this actually minimizes the lapping area and eventually minimize the risk of seepage through all this lapping. So due to the high rib height, the profile can actually cater for more water runoff. So here is another angle where you can actually, what it's showing you is that over the years, even with low roof pitch and changing climates, the profile is still able to, is still sufficient to perform in this climate without any sign of ponding. Even though you see, from this stream tunnel view, it is longer than 100 meter. So we also took some photos of the riverside, meaning below the roof, and there was no evidence of any leakages happening. So that is actually a peace of mind for the whole land. So that is the first point of our design criteria. So let's go on to the second one, which is profile and also building geometry. So now, in my previous webinar, we have shown actually steel cladding can actually cater for more versatile and also daring designs in terms of shapes, and it can also cater to wide arrays of geometries, like this fan-shaped building, or even a more organic structure. But it is also able to provide secure and strong cladding by locking onto the structure. So this can actually be achieved by the wide range of profiles that are actually offered in the market nowadays, which we can actually classify into three major categories: pierce fix, conceal fix, and standing seam profile. Of course, today I won't focus in all these particular one, but what I want to highlight is the second criteria, which is on profile selection and how the building geometry can play a role in affecting that. And we know that the changing climate that I've highlighted earlier, it can actually pose a risk to the buildings that are being designed previously, because the limitation of certain design limit was not taken into account. What are the changing climate, right? So for external cladding, we want to prevent potential wind uplift. Okay, to do so, I'll actually recommend you to consult experts who design the external cladding profiles on what type of design you need. This is because the wind uplift is an extremely complex and fluid condition. And when I mean fluid, it means literally fluid, like dynamic kind of fluid. So to let you know how complex it can be, let me try and explain the best of my each design can actually affect the wind uplift. So before I do that, let me just try and explain better how wind uplift occur and the mechanism behind it. So the phenomena of wind uplift actually occurs this way. So on this diagram, you can see there's wind coming from left hand side, and upon hitting the pitch roof, so the wind itself will actually split into two sides. So the wind that hits the building below the roof will actually slow down, while the wind that goes above the roof will actually accelerate, causing a difference in terms of the wind speed. So if let's say you remember in physics class back then, there's a phenomena called Bernoulli principle, right? So a difference in terms of wind speed can actually create a pressure difference zone, right? So in this specific example, negative pressure will occur on the side with a higher wind speed. So you can imagine pressure like suction. So in this case, the negative pressure means suction or pulling force on the surface. So the whole surface of external cladding is being pulled outward. But of course, not pulling, not every pull will actually detach the cladding, but sufficient amount of force, if let's say it actually overcome the force of locking, then it will actually pull off the cladding. So if the wind speed itself increase due to the strong wind, then the negative pressure will actually increase as well, hence stronger pulling force exerted onto the cladding surface. So to conclude from the first point is that the wind speed will actually affect the force exerted onto the external cladding. Affect means it is pulling it outward, okay, as can be seen from this diagram. So another factor comes in, right? Where if let's say your geometry is changed, then there's another effect to the pulling force. So here I show a research paper that actually compared three types of building geometry. So gable roof, and then the second one is actually a hip roof, and the third one is a pyramidal roof. Okay, so and the wind is coming from the left hand side, and is blowing in the same intensity towards the building. So the one that actually has a drastic, change in terms of the airflow between the one uh, below the roof and the one when it blows over the roof, it will actually create a stronger suction compared to the one that has gradual change in terms of speed. So in this case, the gable roof will have a stronger negative pressure compared to the pyramidal or even the hip roof. So all this can be visualized in the airflow that over here I've drawn out the diagram of airflow streamline. So each wind that is blown from the lowest level to the highest level, right? So what it creates is a zone of negative pressure, as I've highlighted in the diagram. So by creating all this negative pressure zone, the area with negative pressure zone will have pulling force, and the one that is facing the wind will actually have a positive pressure, meaning the wind will actually compress the cladding inward instead of pulling it outward. But by changing the roof pitch, or rather the building geometry, you actually drastically change how the external cladding interacts with the airflow. Okay, so in this case, the one that is highlighted in red font is the one that changed in terms of from negative pressure to positive pressure, right? But in this case, there could be all sorts of other types of changes to the force exerted onto the external cladding, which I dare not say specifically how it will affect the external cladding, because it actually is very, very fluid, and it depends on the type of building geometry you have. Okay, so the best case is actually, again, go back to the expert and address it case by case basis. And come to the third factor, if you have any building openings. So the third factor is, if let's say there is one building opening, but without, so building opening in this case is defined as when it is not defined as door or window, those openings that you can actually close by choice, because during strong wind or strong rain, you normally close the window or close the door. That's the assumption. So over here, they only show one opening that is facing the wind direction. So in this case, you are not only having a wind uplift or negative pressure exerted onto the roof, but you potentially will also have internal pressure exerted from inside the building. So this will actually drastically change how the wind interacts with the external cladding. So upon consulting the experts and determining the wind speed and how it can actually affect or exert pressures onto different part of different area of your cladding, then you can actually know how strong your locking of the external cladding needs to be. Then let's look into the profile locking strength. So if let's say you look at brochures or profiles that has all this detail, technical detail, then it's easier for you to actually refer to, right? But anyway, at the end of the day, you can always refer to all these roof formers or manufacturers to get more information. So in this specific example, you can see that there are tables that they have tested, and the results that are shown in the table here are actually the ultimate pulling force, a locking force of a specific profile. So over here, this table itself is actually showing two profile, the same profile, concealed fixed profile, but in two different thicknesses. One is 0.42 mm base metal thickness and 0.48, in short, we call BMT. Right? So the thicker one essentially means there is more steel material in this concealed fixed profile. And the numbers in the table again is actually a tested result of the maximum force the specific spec can withstand before breaking down or before detachment. Okay. So these tables, we normally refer to the span type of 1200 mm. So the purlin to purlin span is normally at the distance of 1.2 meter. So that's why we refer to 1202 mm. So one of the weakest area is at actually the end span, which is actually adjacent to the overhang cladding. So from what you can see, 0.48 mm BMT shows actually a higher locking force compared to the 0.42 mm BMT. So over here, what you can conclude from this one is, if based on the design and based on the consultation from the experts or engineers, says that the pulling force from a certain area is beyond 2 kilopascal, right? Then perhaps you should consider using maybe a 0.48 mm base metal thickness profile. Okay. And of course, beyond that, there are also pierce fixed or corrugated profile that uses fasteners piercing through the profile to be secure. So this kind of profile, again, there are tested tables, table with tested result also. So here you can see that I'm only using 0.42 mm BMT table. Okay, and over here you can see that they actually did a test with different fasteners, number of fasteners locked onto the profile. So over here, they one purlin, they can lock 3 fasteners or 4 fasteners, and you can see that the force actually is much stronger if, let's say, the fastener is more. So in this case, you know sometimes you should also, when you're doing designing, you should also pay attention to how many fasteners you should actually specify in the specification. Otherwise, if let's say you are looking at cost cutting and you neglected this aspect of design, then you could be in you could be in trouble. Okay, so let's move on to the third point, right? Treatment of unwashed area. Okay, so what I mean unwashed area, and this picture was taken at midday around 12 p.m. and you can see the shadow, right, covering over from the upper roof to the lower roof. So this area that is in shadow is likely considered unwashed area because most of this area is actually not, it is shielded away from rainwater and it would not be cleaned naturally by rainwater. So of course, coming back to the material, we know that material can actually be used and has been used to withstand marine condition or even harsh environment, such as like using it to build jetty or using it to build buildings near the sea, like this building itself. But unwashed area itself could actually potentially shorten the lifespan of all these external cladding. So what is unwashed area? Right. So from this picture itself, you can see that there are actually a side of washed area and a side of unwashed area in the same roof span, right? So essentially, unwashed area means that external cladding that are not naturally washed by rainwater, at the same time is actually exposed to external contaminants or external particle settlement. So over time, you can see that all these areas that are washed, that are exposed to external condition, will accumulate dust or accumulate those particles that are emitted or being emitted around the building. So let me show you some of the examples of unwashed area. So in this picture itself, you can see that the roof is actually a cantilever roof over the building. So the extent of unwashed area is highlighted in the red part, aside from the shaded area. Aside from the screen shaded area. It is not just the cantilevered surface, but also the purlin surface that are right below the cladding. At the same time, also the wall cladding. So areas are normally not washed naturally by rain. So if this building is located near the sea, then there are potential contaminant settlement. So another example here, this is showing a ceiling covering the roof. One part of the ceiling actually fell off, so showing the external, the roof cladding. So from here, the part which is considered unwashed area is only the part that is exposed because of the fallen ceiling. So the part that is still covered by the ceiling is not really considered unwashed area, unless there are large amount of gaps that allow for external contaminant to flow inward and then be settled onto the cladding that is near the ceiling side. Okay. So what sort of external contaminant are we talking about? So if let's say the building is within the marine influence, meaning near to the sea, or is somewhere less than 500 meters and so on, then there tend to be salt particles that are airborne, meaning it is being evaporated with the water, and it will flow inward, inland, and be settled onto any surface. Okay, so another sort of contaminant is industrial contaminant. So industrial contaminant can span a lot, where you can have industries that are popping up in the jungle, and then all of a sudden the surrounding itself will be considered influenced by this industrial contaminant. So some of the examples are like glove industries or sometimes fertilizer industries, so on. So these kind of contaminants, like I said, will be airborne, and you can actually see sometimes a sign of settlements on the wash area. So in this specific case, it was actually near, this building itself is actually near the sea, and you can actually see a very, very obvious salt settlement on the wash area. And here is another example. This building itself is actually near industrial area, where there are a large amount of trucks driving by and so on. So you can see the dust particles settled onto the unwashed area. Okay. Even for the external surface, or so-called the wash area, you can actually see the industrial contaminant. But again, come back to the unwashed area and the wash area. The difference is that for this case, specific case study, the wash area, which actually shows sign of contaminant, was actually the contaminant that are potentially corrosive was actually washed periodically by rainwater. So this kind of cladding, because it's external, the risk is greatly reduced. So the study that shown here actually has been there for more than 20 years. And based on our study, it actually has not shown any sign of severe deterioration. This is another close-up picture. Right. So compared to this other industrial, right? So this is another industrial building. So over here you can see there's actually a wash area and unwash area in this picture. So on the wash area, you can still see sign of staining or dirt mark and so on. So all these dirt marks actually are not rust; they are only staining due to the aging, which is in this case more than 30 years. So the wash area seems fine and still performing, but the unwashed area itself, as you can see from this picture, has already shown sign of rusting, right, on the unwashed area. So the difference in terms of the unwashed and washed area is quite drastic over the years. If let's say the building itself located in marine or industrial environment. So why should we pay attention to this unwashed area? Since the deterioration is quite minimal, as you can see here. So, but if you go upon closer inspection, you can see that the corrosion or the deterioration does not just happen on the external cladding. It actually happen onto any metal surface that are on the unwashed area. So in this case, the pointed out areas are where the fasteners are. And on the roof itself, this is the same building shown here. So if I go closer, you can see that these pointed out areas, these are actually fasteners, but you don't see any connection. It's because the fastener shank has been corroded thoroughly. So the fasteners no longer function as designed because there's no any locking mechanism. So in this case, the wind uplift potential is high, very, very high, because just now I mentioned the locking force is dependent on how many fasteners you need. The more fasteners you have, then the stronger gripping force you have. But in this case, you see most of the fasteners has already been corroded. So there is actually a very, very high risk for these roofing sheets to fly off at any moment. If let's say the weather goes bad one day, or the wind blows in the right direction. Okay, so in order for you to minimize the effect of unwashed area, what you can do, if let's say you have designed or already built a building with a with all these potential unwashed area. So what you can do is put in place a maintenance schedule to actually frequently wash all these unwashed areas. Of course, when I say frequent, it is quite dependent. If let's say you observe all this salt settlement or industrial settlement within 6 months, a heavy one, then you can actually wash down every 6 months. So if let's say it's 1 year, then you can wash down every 1 year. Okay. So, but again, we focus on the designing stage, right? So another way to do it is actually during the design stage, you eliminate the unwashed area entirely. Okay. One of the ways is by pairing up with vapor barrier. Okay. So some of the examples of vapor barrier is like a foil material, where you can actually install directly underneath the external cladding. So there are more examples here. So by actually, installing this vapor barrier, you actually shield the unwashed area from external exposure. Okay, so instead of settling onto the unwashed area directly contacting the external cladding underneath, the salt settlement will settle onto all this foil, which typically will be non-reactive. Right? Sometimes there could be plastic, so it's not as reactive as with contact with metal. Right? In doing so, you also actually are shielding the fasteners from this kind of unwashed area exposure as well. Right? So, of course, by doing so, you also need to consider the durability of this vapor barrier of this shield. Right? Sometimes those foil can be very weak and it can fall off. If let's say a slight error in installation, right, or a slight nudge or a slight wind blowing from underneath, then you need to reconsider the type of vapor barrier that you need to install. Of course, there is also sealing where you can actually use to shield away the structure, the trusses from all this unwashed area exposure. And in this specific case, what they did is they actually installed sealing right below the trusses, and also they installed vapor barrier right below the external cladding. So this sort of like act as a double protection. Okay. So the last point is on immersion area. Okay. So immersion area, when we talk about immersion area, let me just share with you typical wall cladding. Normally we refer to wall cladding. So typical warehouses or buildings, if let's say they use steel cladding, there will be two types. One is they'll have a dwarf wall as shown in this picture, and they'll have external steel cladding on top of that, right, to pair up with the dwarf wall. Right? And another one is where they'll have a direct installation of steel cladding all the way to the ground. So in this scenario, the second scenario here, what happened is that the steel cladding, right, will be either touching or submerged into the soil. So this is what we call immersed area or immersion area. So in this kind of condition, immersion area, normally the platform or the ground that you are in contact with can be considered as the moisture retaining substance. Right? For example, cement that could actually absorb moisture because of its porosity, or even soil that actually absorbs and retain moisture. So all these conditions, actually, the water itself will start reacting with the steel cladding. Right? So here I put a very simple or more scientific way of explaining. So what will happen is that the immersed area it will be exposed to water constantly. And the water pairing up with the oxygen that is available surrounding this cladding will promote reaction of corrosion reaction basically. And what will form is rust. Okay. So these are some of the examples of how you can see immersed area and what is the failure mode. Right, this is directly immersed into the concrete, and this over here is resting on the concrete but directly touching it. Okay, so in contrast, actually during the design stage you should consider is steel cladding with a good clearance from the ground. Okay, so in this specific case, it has been more than 10 years and you don't see any sign of rusting near the end of this cladding because there was no immersion. Here is another example. Okay, so this is quite close. So what happened is that the cladding is actually almost touching the flashing, but there was actually no touching point. So in this kind of area is still not considered an immersed area. So you don't see any sign of corrosion. So in my recommendation, what you should do is if let's say you're designing for a warehouse, right, where you know that the storage itself is something that is powdery or something that would retain moisture or something that is hygroscopic like salt, right? Meaning hygroscopic means the material itself will naturally absorb moisture, okay, just like salt. Right? So this kind of material, if let's say you store it up to as high as can be seen from this picture, then you want to consider building a sufficient height of dwarf masonry wall. And if you want to shield it away from external wind or external factor, then above that masonry wall you can install steel cladding, like the examples I've shown you in the first, the earlier slide. Okay. If, however, you really absolutely need to do immerse the steel into the soil, then what you can actually do is consider treatment on the immersed surfaces, so such as painting over steel cladding. So this will actually provide what we call barrier protection to the surface. So shielding, essentially shielding the steel cladding from moisture, from water, right? And yeah, stopping it from reacting. And thanks again for joining this round of Steel Connect webinar, and I'll see you again